Simple harmonic motion is a very specific kind of back and forth motion. Not all repeating motion counts. What makes motion simple harmonic is one rule. When an object is displaced from its resting position, it accelerates back toward that position, and the further it's displaced, the stronger that pullback is. That resting position is called equilibrium. If the object is exactly there, nothing happens. No net force, no acceleration. But move it slightly to the right and the acceleration points left. Move it to the left and the acceleration points right. The direction always points back toward equilibrium, and the size of the acceleration grows in direct proportion to the displacement. That rule is written as A equals minus omega squared x. Here, x is displacement from equilibrium. A is acceleration. Omega tells you how fast the system oscillates. The minus sign matters. It means the acceleration always points opposite to the displacement. That single equation defines simple harmonic motion. The clearest example is a mass on a spring on a frictionless surface. Stretch the spring to the right and release it. At the far right, the spring is stretched the most. The force pulling back is strongest, but the speed is zero because the mass is just turning around. As it moves toward the center, the spring force decreases, but the mass speeds up. At the center, the spring force is zero and the speed is maximum. The mass keeps moving due to inertia, compresses the spring on the left, slows down, stops, and turns around. Then the process repeats. Notice the pattern. Speed is zero at the ends and maximum at the center. Acceleration is maximum at the ends and zero at the center. Velocity tells you where the object is going. Acceleration tells you where it's being pulled. Over time, the position of an object in simple harmonic motion traces out a smooth sine or cosine curve. The displacement repeats perfectly with a fixed maximum value called the amplitude. One complete cycle takes a fixed time called the period. The motion is smooth because the restoring pull increases gradually as the object moves away from equilibrium. Velocity and acceleration also vary smoothly in time, but they don't peak at the same moments. Velocity is largest when the object passes through equilibrium. Acceleration is largest when the object is farthest from equilibrium. This timing difference is a common source of confusion, but it follows directly from the restoring rule. There's another powerful way to see the same motion: energy. In ideal simple harmonic motion, total energy stays constant. At the extremes, all the energy is potential energy stored in the spring. The object is momentarily at rest. As it moves toward the center, that potential energy converts into kinetic energy. At the center, kinetic energy is maximum and potential energy is minimum. Then the energy shifts back the other way. The constant swapping of energy explains why the speed changes even when no energy is lost. A second classic example is a pendulum. For small swings, the component of gravity pulling the pendulum back toward the bottom is proportional to how far it's displaced. That makes the motion approximately simple harmonic. At large angles, this breaks down, which is why only small swings count as SHM. One final visual ties everything together. Imagine a point moving in a circle at constant speed. If you look only at its shadow projected onto a straight line, that shadow moves back and forth in simple harmonic motion. This is why sine and cosine appear naturally in the equations. So the core idea is this: simple harmonic motion is motion where the acceleration always points toward equilibrium and grows in proportion to displacement. From that single rule come springs, pendulums, sine waves, energy exchange, and some of the most important models in physics.